I love having an idea that's so outside the box that you end up having to create your own metric to even evaluate what you're trying to do. We're going to do that here and a whole lot more, and so much so that in order to just consider the simplest cases of this question, we're going to need 2 videos, so stay tuned for that. I'd love to come back to this topic as well down the road to dive into another related topic called numerical integration, but now I'm really getting ahead of myself. I'm especially excited about showing off some of the ways that an integral can be used, which is a tool that primarily is used to find the area under the curve, but we can use it for so much more than that. We're going to do some serious integrals themselves along the way, so let's get started. Let's take a look at the problem statement here. So we are looking to create the largest possible bowl, and there's a really important simplification or assumption here, and it's a really common kind in an applied math context. So thinking of the clay as very thin allows us to not worry about the tiny variations that would show up in the shape and size of the bowl. Realistically, if you imagine tracing your finger on the bottom of the bowl to the rim, on the inside as well as on the outside, that distance would be a little bit smaller on the inside, right? This assumption, though, of the very thin clay is going to allow us to get rid of that headache. In an engineering or a physics class, you might hear words like massless, frictionless, or even isentropic, all of which can't be true in the real world, but they do sure take a problem from being unsolvable to being solvable. And so what the assumption allows us to do here is to think about the cross-section of the bowl as a path rather than as a shape. And so what we're going to do from that is we're going to use the surface area of the bowl as a proxy for the amount of clay in it, for the volume of clay in it, which is pretty reasonable for a problem like this if you think through what we're doing there. And from that, we can actually make another simplification. So since we're looking for the largest volume, we can assume that the shape, like if you're looking down on it from the top, that shape is going to be a circle. And then the cross-section will be the same no matter which kind of like pie slice cut that you make in the cross-section of the bowl. And so we'll only look at the path starting at the bottom of the bowl and going up to the rim, because that will encode the entire information that we need. And then we can revolve that path around, let's say, the vertical y-axis, and that will describe the shape of our bowl. And we'll get the rest of the way down this list to the word basis in a little bit. But before we try to pick a shape out, we need to figure out what it is that we're going to try and figure out with that shape, right? So I mentioned earlier that we needed to come up with a new metric to decide on different shapes, and so that's what we get to do now that we have a clearer picture of our approach. So what we're going to try to do is we're going to try and make this thing as big as possible. And specifically, what we're going to try and do is we're going to try and maximize the volume of the bowl per unit of the volume of clay, right? But then we said that we were going to use the surface area of the bowl as a proxy for the volume of clay used. And so surface area, abbreviated SA there, that's the ratio that we need to come up with. And how will we calculate each of those? Well, for volume, we already have a ready-made approach, sort of off the shelf from our calculus toolkit, and it's called volume by shells if you've taken an integral calculus class. So integrals calculate the area under the curve by adding up the area of tiny little narrow rectangles. And if we're integrating over our x variable, well then the narrowness is this direction, right? So they're tall and thin rectangles. What we're going to do is the integral to think about that not just as an area but as a volume by taking that little thin rectangle and rotating it around the y-axis. And so how we're going to do that? Well, if you think about the cylinder that you would get when you rotate that around the axis, all we need to do in order to calculate its volume, well, we can actually unroll it, okay? And then calculate a rectangular prism. So the height is the difference between the height of the top of the bowl, which we'll define in a little bit, minus the height of the bottom of the bowl at that point. The width, it comes from the circumference of going around the y-axis. That's 2 pi times our current x-coordinate. And then the thickness is the dx, which is what we call the thickness of that little tiny rectangle. And the thing that is most exciting about this to me, actually, right now, is that it connects to the idea that we made about assuming that our bowl was going to be thin at the beginning of this problem, right? Because if you think about that cylinder, its volume, well, it's going to be dependent on the fact that the outside radius is a little bit bigger than the inside radius, right? But if we make that smaller and smaller, well, the outside radius and the inside radius, they get closer and closer together, and it turns out that the volume is proportional to just the first degree, so that radius to the first power, here our x-coordinate to the first power. And if you're interested in diving a little bit further into that, there's a multivariable calculus topic called the Jacobian, which would help you kind of wrap your head around what the power should be. So we did sort of a loose abstract proof of kind of unrolling the cylinder. That's not like a formal math way of demonstrating that that's true, but we can dive in a little bit further with this idea called the Jacobian if you're interested in jumping in a little bit further. Okay, so let's take a look at the formula that we have here. And so here is our volume by shells. And what I'm calling x1 is the coordinate that's at the left end of our bowl. So if we imagine our bowl looking something like this, okay, we're going to cut it off at some point x1, and its coordinate value that it's going to output is what I'm calling f of x1. Okay, so you'll notice that the height of the bowl, which is described by this f of x1 minus f of x, well, that's the height of the rectangle at any point, right? And then the 2 pi times the x is the radius. I can pull the 2 pi out front because of a property of integrals called linearity. And then the dx on the tail end gives us the thickness. And so that's our total volume expression. So we're going to do the same thing with the surface area, but this one's a little harder to visualize. The expression here is the formula for the arc length of a curve, how long the path of a curve is, but with an extra x tacked on the front there in front of the square root. And that extra x that's baked in there helps us to account for the fact that area, surface area, that's coming from further away from the y-axis, when we rotate it around the y-axis, it has a longer path to take than area that's closer to the y-axis. So I'm asking for a little bit of trust here. Again, if you're interested in diving in a little bit further, the multivariable calculus topic of the Jacobian would help you build a little bit more of a physical intuition for this topic. But we're not going to go much further in here because there isn't as nice of a visual kind of unpacking like we had when we could unroll the cylinder, right? And then what I'm going to do, for the sake of our problem, is I'm going to set this expression equal to 2 pi. And this is basically just classic lazy mathematician here. I want to simplify my process, and so this 2 pi on the right is going to cancel with the 2 pi on the left. This is that forming a basis that I mentioned earlier. It allows us to deal with a situation where we're looking for some sort of ratio or proportionality. So we are picking the amount of surface area as 2 pi, which again is a proxy for the volume of clay. So it's not like I have 2 pi cubic units or of something, right? It's 2 pi multiplied by the thickness roughly. And we're making that thickness really small. So again, it's just representative, but we're picking the basis of 2 pi so that we can just evaluate this integral and not have to deal with any constants along the way. All right, so all we've done so far is derive this metric that I mentioned at the beginning. I don't know, I'm having a blast. I think this problem is fascinating, and I'm ready to jump in and look at our first shape. And so the simplest shape that I can come up with, well, that's a line that runs through the origin. The integrals involved get pretty nasty pretty quickly, and the main reason for that is in that weighted arc length formula that we just looked at, there's a square root of 1 plus the derivative squared. And so if we have anything but the simplest of expressions, that becomes really hard to integrate. Now, that's what motivates the numerical integration thing that I mentioned at the beginning. Again, that's the topic of a future video. So what we're going to do here is we're going to evaluate the line, and then in the next video, we'll deal with some more kind of intermediate integrals that will show up if we use slightly more complex expressions than a line, and then from there we would be forced into numerical integration if we weren't able to integrate something that kind of came beyond the cases that we'll handle in the next video. So now if we imagine a bowl that's defined by a line as its cross-section, well, if you rotate that around the y-axis, you might realize that that's what we would call a cone, right? So we're looking at pretty much the worst design of a bowl I could come up with. No matter what you try and set it down, it's just going to tip over, right? But it's just for argument's sake, it's a nice basis of comparison for when we actually create a shape that's more like a bowl. And the question becomes, though, is do we want this nice tight cone, or do we want this wide open cone? Which of those, per unit of clay, is going to hold the most water? And so not only are we going to need to come up with an expression for the surface area as a function of that a variable, we're then going to need to substitute that into the volume expression, and then try to identify which version of that volume expression as a function of our slope is going to give us the largest volume. So I'm going to parameterize a line by the expression y equals a times x, a being the slope. I can drop the y-intercept because if I shift my bowl up and down, that doesn't change the volume of that bowl, right? However, we are thinking that the slope probably will. So let's get that set up. So let's start with the surface area. So we need to take the derivative to substitute into the expression. So we were going to set 2 pi equal to 2 pi times the integral from 0 to x1 of x times the square root of 1 plus f prime at x dx. Okay? So if our equation is f of x is equal to ax, well, the derivative, We don't even need any derivative rules to work on that. Remember, the derivative is the slope, and since we're talking about a line, the derivative of the line, well, that's just that a value that's attached to the x. Maybe you're used to using an m for y equals mx plus b, okay? And then we set this to 2 pi so that we could just cancel those out. And so what do we have here? We have 1 is equal to the integral from 0 to x1 of x times the square root of 1 plus a squared dx. Well, this is actually really straightforward. 1 plus a squared is just a constant, so we can pull that out in front of the integral. And then the integral of x dx, well, that's just 1/2 x squared, or x squared over 2. And that comes from reversing the power rule for derivatives, which itself comes from this idea of the difference quotient, which itself comes from narrowing down our slope formula onto smaller and smaller parts. Our optimization rescue video, you might be interested in taking a look at to talk a little bit more about that difference quotient. Okay, and that's evaluated from 0 to x1. 0 is not very interesting. We substitute 0 in, it just makes everything go away. And so we just get the square root of 1 plus a squared times, we're going to substitute x1 squared in, and I'll just put the minus 0 there just to be clear, right? So we substitute in our upper bound for x, and then we subtract it with the lower bound substituted in, and that just gives us a 0 there. All right, and I'm just going to solve for x1 now. So I'll start by solving for x1 squared. If you look over here on the far left, there's a 1, and I'm going to set that equal to my expression on the far right here. That gives me 2 over the square root of 1 plus a squared. Solve for x1. You get a positive or negative, but I'm just going to take the positive sense because we're only dealing with stuff that's happening in the first quadrant, in the top right of our graph, all positive values of x and of f of x. And once I square root this again, I'm actually going to combine those square roots and get a 4th root. And then in the numerator, I'm going to have to turn that into a 4. And the reason why I'm going to do that is because I have a 2 here in the numerator originally. It gets square rooted when I solve for x1. And so since I have a 4th root on the right, well, the 4th root of 4 is the same thing as the square root of 2. And that just lets me have it all nicely inside of the same expression. So then I'm going to evaluate that volume expression. And I'm going to take this volume expression, and from here I will substitute in the value of x1 that I got after the fact. And that volume as a function of the coefficient, and then we'll be able to optimize over that a coefficient. All right, so this was the general expression, okay? F of x1, well, remember f of x is just ax, okay? So this is going to be 2 pi, again, integral from 0 to x1. We have an x multiplied by a evaluated at x1, which is just ax1, minus the function at dx, x over here, and we will then distribute this x, okay? So we get 2 pi integral 0 to x1. We have ax1 times x minus ax squared dx. Put those in parentheses as well. That dx is applied to both of those terms, okay? And then we'll get 2 pi, and we're going to increase the power of x by 1. So this will be ax1 times x squared, and then we have to divide by the new coefficient, and then we will subtract. We're going to increase the power of x by 1 and divide by the new coefficient, and then we're going to evaluate that from 0 to x1. Similarly, that 0 bound doesn't do anything interesting. It actually turns out that we get an x1 cubed in both of these terms. The 1/2 minus 1/3 is 1/6. I'm going to multiply that by the 2 out front, which gives me a 1/3. And so the result of this expression is pi times a times x1 cubed all over 3. All right. And then I said I would substitute in the value that I got for x1, okay? So that's pi times a over 3, and then we'll multiply that by, it was 4 over a squared plus 1, and then all of that was raised to the 1/4 power for the 4th root, but then it's cubed in this case, and so we are going to write that to the 3/4 power. So we now have our volume, that's what this was, way over at the beginning, and it's equal to this expression in terms of just the a variable. It's a little bit nasty, but it's definitely something that we can evaluate. So we said we needed to find the largest volume. Well, that's the derivative of the volume with respect to this a variable, and then we're going to set that equal to 0, because remember, the derivative is the slope, and so if we're looking for a maximum, well, if we find the place where the slope is 0, we'll find a maximum or some other point where the slope is 0, but I can say, without going into all the details here, in this particular case, the place that we find when the derivative is equal to 0 is going to be the maximum. All right, so here's a derivative that we've got to take. Well, Unfortunately, we have a little bit of a nasty situation here. This is what's called the product rule because we have two terms that have an a in it. So what we're going to do is we're going to keep the first term the same, and we're going to multiply it by the derivative of the second term. So that is going to be the same expression multiplied by the power on it, and then we're going to reduce the power by 1. And then we have to multiply by the derivative of the inside. Well, we can re-express this as 4 times a squared plus 1 to the negative first power. So that's going to be 4 a squared plus 1 to the negative second power. And then we're going to have to multiply by the negative 1 power that we brought down. So that'll be a negative 4. Okay, I'll put that in parentheses just to make sure it's clear that we're multiplying there. And then we have to multiply by the derivative of the inside of that expression, which is 2a. So this is a big old application of the chain rule that's coming out inside of the product rule. Just as a refresher, if you've taken a derivatives, like a Calc 1 class, that's where this is coming from. And then the second thing we need to do is we need to add to that the derivative of the first term, which fortunately is much more straightforward. Pi over 3 is just a coefficient, so the slope of pi over 3 times the variable is just pi over 3. Just for the same reason that the slope of ax was just a, okay? And then that is multiplied by 4 over a squared plus 1, all to the 3/4 power, and then I said we had to set this equal to 0. All right, nasty derivative. End result of this is a is the square root of 2. I'm not going to bother going through all of the arithmetic, all the algebra there. You can actually multiply through by 4 over a squared plus 1 to the 1/4 power. That will cancel it out in this very first term here, and it'll turn this 3/4 in the second term into a positive 1 power, which does make this problem a whole lot more straightforward to solve. There's a squared plus 1s in the denominator on both sides. That's always going to be positive, and so you can multiply through by a squared plus 1, but there's a 0 on the other side, so that goes away. It's not a terrible algebra problem. It's just a little bit nastier than we wanted to deal with. And that's where we'll stop. In part 2, we'll take a look at the actual volume that comes out of this cone bowl that we just calculated the optimum shape for. And then we're going to look at some intermediate integration problems, which is going to involve some techniques that maybe you've come across in an integral calculus class. We'll also touch on elliptic integrals and a lot more to come. So stay tuned. Let us know, as always, if you have any questions or thoughts.